Hello everyone, welcome back to the series on surface tension and viscosity. I am Rahul, Assistant Professor of Physics, GVPP Government First Grade College, Hagaribommanalli. In the previous session, we have discussed about the definition and meaning of surface tension and surface energy. And we have also seen the relation between surface tension and surface energy. Continuing on the topic, in this session, that is session number 2, we will discuss about pressure difference across a liquid surface, excess of pressure inside the spherical liquid drop, or an air bubble in a liquid. Pressure difference across liquid surface. In this topic, we will discuss about what is the difference in pressure experienced by a liquid surface. See, we have taken three types of surfaces here. Surface A, where the surface is almost a straight line. Surface B, the surface of the liquid is curved inward. And surface C, where the surface is curved outward in this manner. Now, each of the cases here, there will be two types of pressures acting on the surface. Okay, one is the pressure exerted by the liquid. Okay, the liquid which puts some pressure onto the surface here. Okay, we call this as PL, pressure put by the liquid side. So that is pressure applied by the liquid molecules on the surface of that liquid. Then second type of pressure is pressure applied by the air molecules or the vapor molecules. We call it as PV, vapor pressure. It is the pressure applied by the air onto the air or the vapors of the liquid onto the surface. So we will discuss about which of these pressure has how much effect on the surface, which pressure is more, which pressure is less, or if both the pressures are balanced in the all the three cases. And we will find out the pressure difference. That difference in pressures applied by the vapor as well as liquid side is called as pressure difference across a liquid surface. Consider liquid 1, that is in figure 1, where the surface of the liquid is a straight line. Now, for a surface to be straight like this, the particle, let us consider the particle lying on the surface here, it will experiences four types of forces. Okay, one is the force along this side, which is due to the surface tension. What is surface tension? It is the force which tries to keep the surface to a minimum area. So what the surface tension does to this molecule is that it tries to keep the surface minimum. So this molecule will be pushed towards the right by the surface tension here. Similarly, the surface tension here pushes the same molecule otherwise, because again the surface tension tries to minimize the surface area. So this surface tension will push us the molecule to the left side. This surface tension will push us the molecule to the right side. In addition to these two forces, the liquid will also put some pressure onto the molecules in this manner. Okay, so we have PL, pressure put by the liquid onto the molecule in this manner, and fourth one will be pressure put by the vapors onto the molecule in this direction. So a molecule here will experiences four types of pressure from four different directions. As a result, what happens is that the molecules will remain in equilibrium at this straight line spot, and the liquid surface will be a straight line in this way. So we can say that for a liquid surface to be a straight line like this, all the forces must be in equal but in opposite direction. So PL, pressure due to liquid, must be equal to pressure due to vapor. So when PL, pressure due to liquid, and PV, pressure due to vapor, when both becomes equal and they are acting in opposite direction, they cancel each other out and the molecule will remain at the same spot and the surface will be a straight line. So for the first case, as you can see here, if the free surface of the liquid is plane, that is a straight line, then the surface tension acts horizontally in this matter and it has no component perpendicular to the horizontal surface. As a result, there is no pressure difference between the liquid side as well as vapor side. So for this side, the pressure difference is zero. Okay, the pressure difference where the liquid surface is a straight line, the pressure difference will be 0. Now consider the figure B where the surface of the liquid is curved inward like this. That is, the surface is a concave surface. Okay, we know that convex lens and concave lens. So this shape is a concave shape. Okay, if the liquid surface is a concave shape, what is the pressure difference? We have to find out. See here also for the molecule at the center, if you consider this, the surface tension will act in this direction, okay, and the surface tension will again act from this side, that is from the left side, it is along this straight line, okay. So both the surface tensions will be acting to push the molecules on either to the left or the right side. These two balances out and the molecules will remain here. Here, as you can see here, if you the resultant of these two surface tensions will be a force upward. If you draw a parallelogram, due to parallelogram law of vectors, you get the resultant tension upwards like this. Sorry, the resultant force due to the surface tension upward like this. But however, in addition to the upward force due to the surface tension, there will be a liquid pressure. Liquid will also apply some pressure in this manner. Okay. So, in upward direction, there are two forces here. One applied by the liquid and second one due to the surface tension. To opposite to these forces, there will be a vapor pressure. Vapor pressure will be in downward direction like this. Okay, like this, the vapor pressure will try to put the force. As a result, what happens is, now for the curve to be in equilibrium, these two forces must be equal. That is, the vapor pressure must be equal to this pressure, downward pressure must be equal to the upward pressure. Upward pressures here are pressure due to liquid PL and pressure due to surface tension T. Okay, because surface tension is also trying to push the molecule upwards. So vapor pressure will become equal to pressure due to liquid side and as well as tension. So you can conclude that here the vapor pressure is greater than the liquid pressure. Pressure due to vapor, that is this side, pressure due to vapors is more when compared to pressure due to liquids on this side. As a result, if you divide the difference, if you take the difference, you get the pressure, vapor pressure is more compared to the liquid pressure, where the liquid is a concave surface. That is, the concave side of the liquid has more pressure compared to convex side of the liquid. And if you come to the figure C, here the liquid is curved outward, that is the liquid is a convex surface. Now here what happens, the surface tension will try to push like this, as well as it will also take from other side, the surface tension will be in this fashion. So as a resultant, there is resultant force will be downward in this fashion. Okay, here the combination of these two forces due to surface tension will be downward like this, and the vapor pressure will also be downward. Okay, like this. So the force trying to push the molecule downwards will be 2-1. That is, first one will be due to surface tension T, and second one due to pressure of the vapors, that is vapor pressure. And opposite to this, the liquid will try to put pressure in opposite direction. That is, it pushes the surface outward in this direction. So in order for the equilibrium to achieve, again we have to write that for both side the pressure must be equal. That is, pressure due to liquid must be equal to downward pressures from surface tension as well as from vapors P V. As a result, you can clearly say that pressure due to liquid in this case is more compared to pressure due to vapor. Okay. So again you can see here the pressure on the liquid side is more, that is concave side of the liquid. This is the concave side. Concave side pressure is more compared to the convex side. Okay. So we can conclude that for a curved surface, if the pressure difference we have taken, then the concave side will have greater pressure when compared to the convex side. So we can write the excess pressure will always be at the concave side. That is, as you can see here, if the surface of the liquid is concave, then the resultant force due to the surface tension on a molecule on the surface act vertically upward. To balance this, an excess of pressure acting on the downward, the concave side is necessary. That is, the excess pressure will be on the concave side. Similarly, again for figure C also, excess pressure will be on the concave side. Thus, we can conclude that there is always an excess of pressure on the concave side of a curved liquid surface over the pressure on its convex side due to the surface tension. To the next topic, that is excess of pressure inside a spherical liquid drop or an air bubble. See, consider a spherical liquid drop like this as shown in the figure. See, this sphere, let it be of any liquid surrounded by air, or if you consider an air bubble, this bubble is filled with air where the liquid is outside here. Now in both the cases, the surface will experiences again two forces, one coming from the inside, then another pressure is from outside. Now you have to find out the difference in these two pressures acting on the surface of this liquid drop or an air bubble. This will give us the excess of pressure inside the sphere. Why? Because we know that in a concave surface will have excess of pressure. Here concave surface will be this much. So inside this bubble will always be the excess pressure. Now you have to find out how much this excess pressure will lie inside the bubble or liquid drop. Now to calculate this, we will imagine a drop which is divided into two hemisphere, upper hemisphere and lower hemisphere by a plane ABCD. Now this plane ABCD separates the upper hemisphere from the lower hemisphere of the drop. Okay, and let this sphere has radius r. Since the radius is r, the circumference of the circle ABCD will be 2 pi r, and the area of this plane will be pi r square. Let P be the pressure, that is excess pressure inside the liquid drop. Now we will neglect the weight of the drop, that is we will neglect the impact of gravitational force on this liquid drop, and we will consider, if we neglect the gravitational force, there are only two types of forces left. One, by pressure exerted by the inside the bubble on the surface, and second one pressure exerted by the surroundings onto the surface. So totally there are two forces. First one, we have outward force on the plane of the surface AB due to excess pressure B. Outward pressure will be here, which is put by the liquid onto the surface, or in case of air bubble, put by the air onto the surface. This excess pressure. Now this is applied onto the surface, so we will take it as F outward, force outward. Now which we know that the pressure is given by force per unit area. So force will be pressure, which is excess of pressure, into area. Here area will be area of the circle, because we have taken for the upper hemisphere, we are calculating the force output. It will be given by P into pi r square area of the circle, and excess of pressure is denoted as P here. Now force can be calculated now. See, we have discussed from previous concept that for a liquid drop curved like this, the inward force will be because of two components. One is vapor pressure, which pushes the surface inward like this, and second one is, if you consider a molecule here, this molecule will experience inward force because of the surface tension in either of these two directions. So surface tension will push the molecules in these two directions. Resultant force will be inward in this fashion. So total inward will be due to vapor pressure PV as well as surface tension. But however, for a liquid drop, the inward pressure will be from the vapors will be on all sides. Okay. So all the sides V pressure will be there. Therefore, the pressure due to the vapors can be neglected here, and the only force which is pulling downwards is due to surface tension. Okay, from the definition of surface tension we know that it is force per unit length. Therefore we can write force which is inward here, F in equals to surface tension into length. Instead of length we are taking sphere, so we will take the circumference of the circle, which is F in equals to 2 pi r into surface tension T. And since this entire hemisphere is in equilibrium, this is possible only when force outward is equals to force inward. Substituting the values of F out and F in, you get pressure P as 2T by R, where this P is the excess pressure inside the sphere, inside the air bubble or the liquid drop. So that completes excess pressure inside a liquid drop or air bubble. This session here, and in the next session we will discuss about angle of contact and capillarity. Thank you.